Hello, Squidlings. I'm meeting up with my friend Aliona. We actually just met in Los Angeles about a month ago when I was in Los Angeles. Our mutual friend Ben has started a makerspace where he teaches people to do arts and crafts or some mechanical engineering. And I met Aliona, who has her own YouTube channel. She's not just Aliona, she is also Dork Matter Girl. Would you like to introduce yourself?
Yeah, thank you, Ted. It's really nice to do this joint conversation, joint video with you. Hi, guys. So it's Aliona, or I have a channel, Dork Matter Girl. I have background in astrophysics and software engineering, but my YouTube channel is just kind of a combination of scientific theories of consciousness and some of the emerging technologies. So I'm really happy to be doing it with Dad. I am also aspiring to be a PhD student in the future.
We just recorded another video, which is going to be on her channel, Dork Matter Girl. We were talking about quantum computing. And while we were talking about quantum computing, it seemed like I was getting deja vu because there's so many topics in quantum computing which are so closely related to what I'd like to talk about, reinforcement learning. You'll notice the date underneath the title there is November 9th of last year. That's because I'm reusing a presentation that I gave to a class of Professor June Tani. Um, so I would love to talk to you about reinforcement learning. I'm going to share with you four kinds of reinforcement learning, step by step. Aliona, I'd like to know what you know of reinforcement learning before I start.
It's an algorithm, unsupervised type of algorithm that, particularly the way I imagine it, as you have an agent or a system that attempts to do a bunch of random actions, and it has some way of measuring its own success. So it wants to maximize its success. Say if you have a little dragon jumping over the hoops, it starts random, but it will pick the action where it jumps over those. I also think of it as a evolution type algorithm. So you want the survival of the fittest dragon kind of situation. So that's kind of the extent of my knowledge.
I think that's just about right. I think sometimes I hear it called self-supervised. So it's not quite supervised. It's not quite unsupervised. It's self-supervised. So if I just click on this screen, it should go to the next slide. There we go. So what is reinforcement learning and why? Like you were saying, it's a machine learning algorithm to teach agents to perform tasks by choosing actions which maximize rewards. Reinforcement learning has been used in a lot of different situations. It can beat humans at chess and Go. I don't know if the most famous examples of robots which play chess or Go are reinforcement learning, but you can use reinforcement learning to do it. And ChatGPT is just a natural language processor, except sometimes when you use ChatGPT, it says something like, sorry, I can't do that. And if I understand correctly, that sort of is implemented with reinforcement learning, where you tell ChatGPT, no, you're not supposed to say that sort of thing. Which I think is in a lot of situations, maybe that's for the best. So let's try making something a lot simpler than chess and Go. Let's go to the easiest thing we can imagine. So this is a game you can play with a Python package called AI Gym or Gymnasium, uh, and which asks the question, how do you keep a pole elevated? Just moving left and right to keep that pole pointing upwards. As a human, how would you think of doing that?
All right, so I guess I'll move to the left if it's falling, and then if it's leaning against it, I will do the reaction of moving back, and then if I move too much, I'll move a little bit less. So basically, reactionary adjust every of my next action to the combination of the previous actions, where I know if I move too much, then it will fall. So I will do that until it balances.
That's, yeah, exactly what I say on the next slide, where I say, well, I think I would consider what I'm observing and then choose actions which I think, based on experience in the past, will maximize the pole's future time upright. So I added some text there where I say, oh, I'm leaning to the right. Let's push to the right so that the pole is pointing upward again. Or you can do the same thing with pointing to the left. In this particular game, there are only two actions. It's a discrete action space, which means you can only move to the left or move to the right. There's no actual staying in one place. So how can we put this in computational terms? I believe I stole this image from someone in my lab. Their name is Donchi. And I think this looked a lot like a slide from your presentation that you just gave, where we have a state coming from an environment, and the computer sort of considers the state, and it chooses an action, which it hopes will maximize its reward. How does that relate to the slide that that I'm referencing?
Yeah, that's actually exactly what that slide was about. It was about the process of machine making an action in an environment, from like, so basically the process of machine operating itself in the environment, and then that slide was specifically for us to discuss in which state, in which stage of that process quantum computing can come in. Can it come in at the level of action? That would mean actually completely different, something we didn't discuss, where it will, I guess, like have some type of quantum robotics like mechanism on its hands, or some ways that I can imagine. Would it come in at the process of calculating state, which is on the sensor, I guess, or algorithms to collect data, or on the state of calculating the reward? So that's just, yeah, that's very similar to the discussion we had before.
Yeah. I think later we're going to talk about something where we are applying randomness to actions.
You can use quantum mechanics to teach robots to navigate in the state of uncertainty. What would that mean to teach robots about uncertainty?
I am so glad you brought that up, because I think that's very closely related to Friston's free energy principle, which is sort of what I'm trying to get a PhD in. I don't go into Friston's free energy principle in this slideshow, but I'm trying to publish a paper. I submitted the paper about 2 months ago, which means they should be getting back to me with things they want me to revise. But the Friston's free energy principle is all about uncertainty. And when you understand some parts of the environment but don't understand other parts of the environment, then you might keep going to those parts of the environment in a way which is based on Bayesian statistics.
That is something I really want to discuss more in depth, but I guess we can leave it for our next conversation.
Yeah, if you start me getting into Friston's free energy principle, I might not be able to stop.
That's something I want to get into.
But I do touch on something related.
Okay, yeah.
But just to get into the most easy kind of reinforcement learning, let's build an agent to play the cart game, the Cartpole game. So first we need to talk about Bellman's equation. How do we consider rewards, not just here and now, but also in the future? So we call that a state value function. So you can see this, the value, v, given a state, is equal to the reward of the state given the best action, the max action, plus gamma, just something between 0 and 1 telling us how much we value the future, um, with a probability which says this is the next state. So given this state and that best possible action, we're going to get this new state. And then what do you do after that? You find the reward of the state after that, based on new max action. So you can see that this just keeps going on forever. You're in a particular state, and then you can look as far ahead as you want. So in order to simplify this, let's condense those iterated steps, because it's all nested. So let's find a way to compose them. So this is a much simpler version of it, which implements itself, where the value we associate with a state is equal to the reward of the state and an action, plus expected future values given the best possible action. So I believe after that it says this leads to the state action value function, which I talk about on the next page. I think I was overwhelmed when I saw this for the first time.
Let me just kind of try to understand it and rephrase it in my own words. So you're saying that
Sure.
this function helps us consider not only the reward I'm going to be getting by taking the next action, but the reward I'm going to be getting taking all the potential future steps. So that's where this, I guess, like some.
But I think what really matters is that it's nested. So we have the value, but the value contains expected future values.
But does that mean that, okay, this value for my next step contains all the future values, so then the step after it will contain all the future values also?
Yes, absolutely.
Okay, interesting. But what is it takes from the past actions?
So I guess if we're playing basketball, then I don't get any points by dribbling the ball and running to the opponent's hoop. The only way to get a reward is by actually throwing the ball into the net, which means that there is value in dribbling the ball toward the opponent's net, but you don't get the reward from that action. You only get the reward some step down the line.
Okay, I think I kind of started to get especially I guess my last question. So with R, that is the function of S and A, that should evolve with every step. Does that change, or is it staying the same?
Yeah, it's the same every step, because I guess in the basketball example, in basketball you get a point, or 2 points or 3 points, when you put the ball through the net. And that's always the case. So I'm not getting any points when I dribble the ball to my opponent's net. But in order to put the ball through the net, I'm going to have to do that, even though I don't get any rewards immediately.
Okay.
So that's the relationship between reward and value. I believe this next slide has a lot of computations on it. Well, actually, here we can see some variables. I hope that this is large enough to be readable.
Yes,
how
I
we're
can
doing
see
this.
that.
But we have a variable which is called st, the state at time t. In Cartpole, there are 4 parts of the state. There's a position, a velocity, an angle of the pole on the cart, and the angular velocity. How far is the pole moving in one direction or another? Then there's another variable, the action, at time t, which is just pushing to the left or pushing to the right. It's discrete. There are only 2 actions. Then there's another variable, r, at time t, which is the reward you get by doing that action at that state. In Cartpole, this kind of confused me. Cartpole, you get a reward of 1 every single step of the way. because your goal is to maximize the number of rewards you get overall, which means you have to keep that pole as balanced as you can. Does that make any sense? It's a little weird.
No, that makes sense.
And then the last variable here is done at time t, which is 1 if it's the final step, or it's 0 to say we're not done. And in Cartpole, the episode ends when the pole falls. So in order to maximize rewards, you have to keep the pole up for as long as you can.
Wait, that's something that doesn't make sense. Why can't I just stand in place? If I stand in place, the pole stands in place.
Well, remember, there are only 2 actions. It's pushing to the left or pushing to the right.
But that's what I'm
which
wondering.
Means you can't actually stay in.
But why would anyone invent such a stupid game?
I think that's just the challenge. So they can teach people reinforcement learning. Well, this isn't the only game we'll talk about. Maybe you'll like the other game more. But if I make a little clarification, the state at time t, the state represents all information in the environment. So in something like Cartpole, a Markov decision process, where given this state, you make an action. But there's an alternative to this called a partially observable Markov decision process. And in that case, there's still a state, there's a complete environment, but the agent doesn't actually get to see the entire thing. So maybe the agent has eyes, and then it's what it's experiencing depends on what it's looking at, but the whole state is still there. So that's another way you can make it even more complicated if you want to. Man, what's going on here? It's been a while since I've given this presentation, so I'm not completely sure if I remember everything here.
I actually have a question for you. This is like a stupid game because like in reality I can just stand in one place and like I don't need to move. But can you think of any example more like intuitive where we as humans use reinforcement learning? So like intuitive, I understand that the problem is that you have to take the next action. You can't just stay in place and like but like what would that be in an actual environment?
I don't know if this counts as an actual environment, but chess.
Oh, okay.
I believe there's a German phrase about the best option being not actually doing anything, but that's not an option because in chess you have to make a move. So that's a lot like this example of Cartpole where you have to move, and it might not be exactly what you wanted.
Wait, this is completely branching out and a little bit philosophical, but like we never touched on it. But what's human brains like? Are they anything like reinforcement learning, or are there like way more complex algorithms that lay behind our brain functions for the decision making?
I'm guessing it's a lot more complicated than reinforcement learning, but I'm sure that reinforcement learning might be the best way that we can simulate it at the moment, especially when we get into the really interesting stuff like Friston's free energy principle.
You've been intriguing me with that one.
Oh, if we do this again, I have to talk about Friston's free energy
principle.
I
would love you to.
I could talk about it for hours.
I would love you to, please.
But I might need to publish that paper first because I think my paper is a really good example of why it's so powerful. Gosh, I want to publish that. But if we go over here, here are some equations which we implement in reinforcement learning. So in theory, there is an optimal policy. It's the action value, which is maximizing Q. Oh, well, what's Q? Q, well, there's a Q with an asterisk next to it, meaning the optimal state action function, which is sort of the Bellman equation that we were just talking about. So the optimal state action function is calculating the value in the perfect way, even though it's a really complicated thing which involves so much in the future. And so, in order to approximate this, because we don't just have access to it, we have Q with a pi hypertext, which is the state action function for the policy pi, which is sort of trying to become the optimal policy. And you can see that it's predicting the Bellman equation. It's trying to predict the reward it gets plus future rewards, unless you're already done. If you're done, then you don't have to consider the future anymore. So in this little example, if this Q value, this Q function, is considering what kind of value it would get if it pushes to the right when it's leaning to the right, well, that's a better value than leaning to the right and pushing to the left, because if you push to the left, then the pole is just going to collapse and you're not going to get any more rewards. So depending on what you think the values would be based on every possible action, well, that's how you choose the best action. We call this a deep Q network because the Q value is the value that we're trying to approximate, which chooses actions maximizing not only the reward right now, but future rewards. So a deep network is one way to do reinforcement learning. I think the next page, I might want to skip this one. This is a pseudocode plan, which I also stole from my friend Donchi. In the beginning of reinforcement learning, when you've just made the robot or the model, you often choose actions at random.
Yeah.
Because that's one way to make the agent run around and figure out how things work. If you're not using the probabilistic model, then you select the best action the action that you think is the best. It maximizes the Q function.
Mm-hmm.
Then you do the action, the environment gives you a reward, and the next observation. We can store the whole thing, the whole state, action, reward, next action, in the replay buffer. And then in order to actually train the model, we take a whole bunch of memories and try to predict what those values would be.
Mm-hmm. It makes sense to me. I mean, as a pseudocode, I understand the general kind of strategy. You have to actually code it with mathematical methods. I'll leave it to someone else, but I get the overall idea. I did want to ask you a question though. I was thinking, you did give an example of environments where this type of algorithm succeeds a lot, like chess, or this problem with the thing moving back and forth without stopping, which I think is not a realistic type of problem. But it's okay because that's, I guess, how you can, the simplest way to explain it. But what are the type of environment?
No, I think you're right.
But what are the types of the environment where this algorithm doesn't perform the best? Like, can you think of any?
I'm so glad you asked. I'll cover some other models based on problems that this model can't really solve.
Interesting. Okay, I'm looking forward.
If you can wait a few slides, if you wait a few slides, we'll figure this out. I have a GitHub example.
Mm-hmm.
So if you go to Ted Tinker RL example in GitHub, you can just find the code.
But the random threshold is just kind of a hyperparameter. You can set it initially to whatever you like.
Yeah, if we set it to 0, then there wouldn't be any randomness in the beginning.
Right, so you set it to almost 1, like 9999. So, okay, I mean, I understand the the high level. I'm not gonna probably. I mean, I might implement it in the future, but I don't think I will. But I understand this is like a very specific guidance of implementation of the algorithms that we discussed as a pseudocode before. So yeah, that makes
Yeah,
sense. Thank
this
you.
is a very specific thing.
Yeah.
So there, I think when I end this presentation, I say there's so many different ways to implement this, and they all have their advantages and disadvantages. But I'm also glad that you bring up the randomness, the random actions, because that's something we solve later. You don't necessarily need to have those random actions. But you can see the results. Just based on episode durations up here, they're getting better. That's the rolling average is the red line. So it's getting better and better over time. On the left, you can see this idiot, this agent. It's just sort of moving in random ways, and eventually it falls over. But over here, after a lot of training, it manages to stay up for almost 500 frames. So and that's not so bad.
How many iterations did it take him to?
He saved.
In order to stay, in order to evolve from 24 to 499 frames.
It looks like it took 1,400 episodes. It's hard for me to tell exactly how many times it trained because it trained every step. Okay. So it did a lot more training these really long-lasting episodes. I think it took 10 minutes.
Oh, wow.
Which is a bit, it seems a bit long considering how simple this game is. What if we have a partially observable Markov decision process? So in this next slide, let's have a deep Q network with recurrent layers. So when you have a recurrent neural network, it gets an input, but it also has a hidden state, which represents its impression of everything it's seen up to that point. So you can have an environment. It provides states. The states also give you a reward based on your action. But the states are also used to update your hidden state. So as if we're considering what's happened so far. And it's from the hidden state that we get a value. And then comparing the value to the reward gets you the error function, which lets you increase the model, and eventually choose an action based on these hidden states. What do you think of that? I think recurrent neural networks are difficult to grapple with at the beginning.
So the hidden state is the one that gets updated, right?
Yeah.
And it gets updated based on the next iteration?
On the next state. Oh. So when we get a new state, then we put that input in, and also put the hidden state in as an input, and it's producing a new hidden state.
But with these hidden state, the hidden state is kind of like a neural network. Is that like, or sorry, it's like a layer of the neurons with values. Is that right? Or like a tensor?
I think a good example for this might be in ChatGPT. If you ask ChatGPT a simple math problem, it might be able to solve it. But I've seen people ask ChatGPT to purposefully get a question wrong. And then ChatGPT says, okay, I'll get the next question wrong. And then they ask, what's 2 plus 2? And it says 5. And obviously it could solve the problem, but it had a hidden state which reminded it, oh, in the past I was asked to do it wrong. So the agent has a conceptualization of the world that changes over time. And it's not throwing information away, it gets to keep important information. So let's try Cartpole, but we won't let the agent observe velocity or angular velocity. So it can only look at its position and the pole's position. That's important information, the velocities. So the deep Q network we'll have to derive them from previous steps. Oh, and also I have a GitHub repository where I show you an example of that. I'm so glad I made those GitHub repositories. I think that I do a lot of coding, and I need to make sure I put that out there. I also should say that the hidden state, we toss it out whenever a new episode begins. It doesn't need to remember stuff that happened in previous episodes. That's not really information. Thing which does change a bit is the training. Sorry, go ahead.
Why wouldn't it need to remember what happened in the previous episodes?
When we train the model, it's learning how episodes carry out. But once the model, the Cartpole has fallen and the episode ends, the agent isn't getting any advantage by knowing where the last episode ended. When we play a game, we improve. We improve when we play the game. But when we start a new game, you don't need to remember what happened in the last game specifically. The improvement of what happened in the previous game would be applied to the parameters of the model.
Oh, okay.
When you start another game, the scores are reset, and it doesn't help to remember what the scores were at the end of the last game.
Okay.
I don't know if it's working as well. I think it took longer to train to this point, but it's working. Yeah.
Oh, okay. So it was your implementation.
Which is nice because it doesn't know velocity. It has to sort of calculate its velocity, and I think that's really cool.
Yeah.
Well, I think you'll enjoy the next part because you didn't like the Cartpole situation. It's not a realistic, natural situation, and part of that is because Cartpole only has 2 actions. It gets to consider all of the possible actions because there are only 2 of them, and then pick the better one. So what if we're playing a Pendulum challenge where there's a reward based on pointing the pendulum up? But this time, the agent, it's not just pushing left or right. It also chooses the strength of the push. So a deep Q network could let, because there are an infinite number of possible actions. It's a continuous action space. So in order to do this, we're going to need 2 models. We're going to have an actor generates actions, and a critic which judges the actions. So I believe I also stole this from Donchi, and it's more or less the same as the last image we looked at, like this one, except there's a policy function, the actor, which makes an action based on the state, and the value function, the critic, which pictures out the value based on the state. Donchi's looks like it only uses the state. I employ the state and the action. So the actor is trying to choose actions which impress the critic. He wants to impress the critic, and the critic is trying to be as accurate as it can. So here we go. I already have an example at RLAC example. This only has to make 1 value because it's given the action. Or there's only 1 action being performed. And then the results. And unfortunately, I couldn't figure out how to render the pendulum. I was getting so many problems rendering the pendulum. But it looks like it's doing okay. The rounding, the rolling average rewards, they went up. I hope that's decent enough. So any questions about the actor-critic method before we go to the soft actor-critic?
Tell me the difference, because I never understood the difference, really.
Between the actor-critic and soft actor-critic?
Yeah.
I believe it might be on the slide. Oh, almost. Well, okay, so far we've given the agent initial data by having it explore with random actions. That's very inefficient, especially when you have a continuous action space, because you're not really figuring out, but you can't cover all of the actions. There's no way to cover all of the actions. Or if the rewards are sparse, meaning that most of the time you're not getting a reward. Your reward is equal to 0. For example, in a basketball game, because in basketball you only get points when you make a basket. The rewards are 0 most of the time. Instead, we can encourage exploration with intrinsic rewards. The rewards that we've been talking about so far are extrinsic, meaning defined by humans based on what we want the agent to do. There's another kind of reward, intrinsic rewards, generated by the agent based on other goals, like exploration. One of them is entropy, and that's in the soft actor-critic method, which can choose its own random actions. I'll talk about that a little bit more on the next slide. But there are other kinds of intrinsic rewards. Curiosity is the one I'm more or less trying to get a PhD in. Novelty, which I think is just another definition of curiosity.
I really wanted to talk more about curiosity and then novelty specifically for scientific explorations. Not just like an artificial environment like chess or whatever the pendulum situation is, but like a real environment of reality that doesn't really have the finalized rules that we know. So can you, by applying those methods of intrinsic reward, which I guess like is motivated by curiosity and seeking some form of novelty, like, so I want to kind of figure out if you can apply that towards the real environment.
I think absolutely. I think the pendulum and the Cartpole, they're metaphors. They're metaphors for reality. In reality, robots will still get states, they'll still get observations, and they'll still have to choose actions. And so I think the really simple ones are simple ways to explore things that work in real life.
Yeah, but the question is, can you utilize this method for the real world exploration, scientific exploration, with success higher than human mind can offer? Whatever you have the scientific method right now that is driven by primarily human mind and whatever tools we have, versus the utilization of robotics, like robotic labs with that kind of method. Is that even feasible?
Well, I think a lot of scientific discoveries happen by accident. I think antibacterial stuff only arose because someone made an accident along the way.
Yeah.
So I think entropy is a really important aspect. Suppose the actor doesn't deterministically make an action. Instead, it makes a probability distribution and randomly samples an action from it. So the way we do that is it produces a mean, it produces a standard deviation, we multiply the standard deviation by something random, and that makes the real action that it chooses. And then, in addition to extrinsic rewards, the agent is intrinsically rewarded based on the negative log probability of having chosen that specific action. So that means, well, if the agent doesn't know how to get extrinsic rewards, it can intrinsically reward itself by moving around in random ways. And that can make it a lot more likely to find the extrinsic rewards. So for example, babies. Babies don't know how to do anything. And so they're thrashing around and saying nonsense. But that's the way they start, and eventually they'll grow into toddlers who can move around. I believe there's one more. Okay, so there's an example on GitHub of a soft actor-critic.
That makes sense. Yeah, I guess example of babies is just kind of stuck in my mind because it's interesting. Does that mean that you think that babies have a combination of intrinsic reward with like some form of extrinsic motivation?
Yeah, I think over time, babies, like when babies discover lollipops, sugar, that's an intrinsic reward. It wants a lot of that. But the only way to get there is by finding something new. I think curiosity is often a more interesting, but entropy and curiosity are both derived from Friston's free energy principle, actually.
Mm-hmm. But we're not gonna
let's not this time, but maybe next time. If I keep going, so the results, I think they look about as good, about as good as the other ones. Reinforcement learning can be implied in a lot of different ways, which have different advantages and disadvantages. The most challenging aspect is exploration, because you need to have the information before you can exploit that information. So exploration can be performed randomly, but that's not very good. Encouraging it with intrinsic rewards like entropy or curiosity that I'd like to maybe cover next time. Those are the most important ways to do it. So reinforcement learning is challenging, but when it works, it really works. So thank you for listening. I'm sorry that lasted a lot longer than I thought it would.
No, I'm very glad that you went into all these details, even though maybe some of the parts I didn't fully understand. I appreciate that. I'm sure it's gonna store somewhere in my subconscious, and then I'm gonna get back to it. I did want to learn the definition of entropy in physics is like completely different, or not completely, but very different from what I kind of like understand that definition is entropy in reinforcement learning.
Entropy and curiosity have a lot of different definitions in different fields of science. So that's a great thing to notice.
And I think I really, for the next time, I really want to discuss free energy principle, and also I wonder if we have some time stop on entropy, because I feel like the free energy principle is a little bit related to physics. And then the entropy, I want to discuss the difference because you clearly have some understanding and the interpretation of entropy that maybe is a little bit different from what I'm imagining.
Yeah, the next time we meet, I'd love to share a paper that I think was hugely inspirational, and I might be piggybacking off of this paper for my PhD's first paper, where they come up with a definition of curiosity based on the free energy principle. So in addition to entropy, you can also have curiosity. And I think curiosity is a little bit more complicated than entropy, but it works. What's most interesting is that entropy and curiosity work best when you combine them.
That sounds very promising. I'm actually fascinated. I mean, because for me, okay, free energy would be something that I can understand in terms of thermodynamics. And then curiosity is something completely separate that I would attribute to like philosophy. And here you are coming up with a certain definitions that are like combining these. So I'm very curious.
That phrase appears in physics. And it's not the kind of free energy where you violate the laws of thermodynamics. We're not making free energy. But it also is a term in Bayesian statistics. And I've heard that the physics definition and the free energy principle Bayesian statistics definition are actually closely related in a way that I don't understand.
Well, I think I'm gonna also read and prepare for the next time to kind of better understand. Okay. So, like, I am very grateful. That was super interesting, and I know you put a lot of effort.
Yeah, if you want to look more into the code, it's all on GitHub.
I like philosophical side. That's why I was asking you so many questions, because I recognize that it is hard to implement and there's certain methods, but it's just the type of personality that I have. Like, I know how to code, and I do it was like, oh, okay, let's do that. Fuck, I gotta implement. But that doesn't excite me as much as, like, oh, let's discuss the philosophy and
Yeah.
abstracted level of it. Because, okay, so that's why I pushed you a little bit towards philosophical side. So I apologize.
I'm glad that I'm glad that the talk became more philosophically interesting as we went along, because the first thing, the Cartpole, that's not fun at all. It's the most boring example you can find. But as you go deeper and deeper into it, there are ways to do more philosophically relevant things.
Yeah, I agree. And especially as you talk about your PhD research, that one is extremely intriguing.
I am desperate to publish this paper so that I can make a YouTube video about it. I'm not supposed to say anything about it until it's out.
When is it going to be out?
I can share a paper that my paper cites.
Okay.
We're not sure. I think I said I submitted the paper about 2 months ago, which means they should be getting back to me with either we're publishing your paper, or we're never publishing your paper, or revise this stuff and send it back to us.
Oh, which journal are you trying to publish it in?
Neural computation.
Ooh, okay.
And it's not just reinforcement learning. They also cover a lot of biological learning, which I think means it's the perfect sort of balance where there are a lot of people reading it who know a lot about one thing or another thing, and they really want to see the intersection of those concepts.
Right. I mean, I'm sure it's going to get published, or you're going to just change a little bit, revise it, and you're going to get published.
If it's not published, well, then I can just make a YouTube video about it.
I'm sure it's going to be published. Plus, a lot of us are waiting for your YouTube video to be available after your paper is done, so keep us posted.
I think a lot of my subscribers are waiting for that, and sometimes I play Team Fortress 2 instead. So, but thank you so much for having this conversation with me. This was really something. So Squidlings, go to Dork Matter Girl, her channel, and on her side of the channel, actually, you can see the two of us specifically talking about quantum mechanics, or quantum computation, which is also a really interesting concept, which I think is related to the free energy principle. They're both based on Bayesian statistics and statistics in general. So it's really interesting seeing things just sort of meshing together eventually.
I guess we're right on time, which is good for me. We're right, actually, 9:29, and I was supposed to be done by 9:30, which is right on time.
Okay, perfect.
Thank you.
Well, I'll send you an email, and we can figure out how to do this again. And,
yes.
Until then.
By the way, I've got a Patreon at patreon.com/Thinkster. I want to thank all these squidlings and elder squids. Thanks.